Ladies and gentlemen, boys and girls, this is our final lab of the semester, Lab 10, Ensemble Models. This lab is going to be fundamentally different from labs you have done to date in that you will be submitting your final results into a Kaggle competition. The goal will be to predict house tax prices based on a Zillow database that was created about 3 years ago. So first and foremost, go ahead and if you hop onto Blackboard and you look at the actual quiz, you'll see that this week's quiz is a little bit different from the past. First and foremost, there's only one question. And this question, all you will do is you will upload the final code that you create as a part of this assignment onto this, and then you will save and submit. However, your grade will not immediately be revealed to you because the way your grade will be calculated is going to be based on a submission to Kaggle. So let's go ahead and copy and paste this URL, and we'll hop over here into Kaggle. Now, you may have to create an account for this. If you have not ever used Kaggle before, you do need to register an account. Use your William and Mary ID. As you'll note here, as I write about this, if you need to create a Kaggle account that has your name and your William and Mary email address associated with it. Otherwise, I may have to email you to figure out which Kaggle submission is yours, and if I have to do that, I will be sad and I will take points off your grade. So that is very important. Please do remember to do that. Back over on Kaggle. So once you log in, you will see something that looks a little bit like this. Now, how Kaggle works is it's essentially a competition website for data scientists. So it's a website that allows you to upload data sets, run analyses, and compare how good your predictions are relative to other individuals. So once you log in here, what you'll want to do is you'll want to first go to data. And so here you'll see this is the actual data that we'll be using in the lab. In this case, we have 3 different files: sample.csv, test.csv, and training.csv. Sample.csv is an example of the format you will need to upload your results in, and I'll walk through more detail of that in a moment. Test.csv, this is the data you'll be predicting to. Training.csv is the data you'll be fitting your model with. So test.csv does not have any of the kind of truth values, whereas training.csv does. So your goal will be to estimate the home tax amounts in test.csv where you don't actually have that column of information. You will not actually ever have that column of information because what happens is when you submit your predictions up here later on, Kaggle will automatically tell you how accurate you were. Now, that will show up here on the leaderboard, and you'll be able to see here over time how well your particular submissions are. But we'll talk about that in just a moment. So back on data, I'm going to click on Download All right here, and we'll go ahead and save this somewhere I can access it. So in this case, I'll save it under Ensemble Lab on my desktop. And then I'm going to go ahead and open up this particular zip file. So this is just the zip file. I'm going to go ahead and extract these 3 files. So the sample, test, and training.csv, and I'll put these in that same place, that Ensemble Lab. So, okay, there we go. So you'll see that there are 3 files here again. Importantly, test.csv, this is much smaller, around 20 megabytes, whereas training.csv is around 240 megabytes. This is because the training CSV file we'll be using is around 1 million rows of data. So this is a fairly large lab. Once you have that data downloaded, go ahead and hop into Jupyter. And then let's go ahead and create a new Jupyter. Well, we'll create a new folder in this particular case. I'll name it. And then I'm going to upload those 3 files. All right, so now I'm going to go ahead and open up a new Jupyter notebook. And we'll go ahead and get started here. So first and foremost, let's go ahead and grab pandas and random. And we're going to load in the training data that we just downloaded. Importantly, because that training data is around 1 million rows, for the sake of this video, I will be using a much smaller set. I'm only going to be using 10,000 rows. Feel free to experiment with larger numbers of rows. The way that we'll do that is through something called row skipping within pandas, and that's fairly straightforward. And there we go. So now we have this imported. We can take a quick look at BCA to see what we've got. And there we go. So this is the data frame. So you see there's a lot of NA values, but ultimately we see a couple of things that we really care about. First is the ID. So every single one of these is going to have an ID. And then tax amount. This is ultimately what we are trying to predict. We want to see how much tax a house has to pay based on a wide variety of other characteristics. Does it have a deck? Where is it? How many bedrooms does it have? Trying to get an idea of how the assessed value is associated with all of these different criteria. So let's explore this just a little bit more to get an idea of what we're looking at. Okay, so there's three different things here. First, we have the shape. So this is there's 10,000 rows, 58 columns. These are the names of all of the columns. Now, one thing you'll see that I'm doing here, this dta.dtypes, this is new. This will tell you for every single column what type of column it is. So a float, some sort of decimal value, objects, which can be a wide range of different things, and then integers as well in the case of the ID field. We have to be a little bit careful here. For example, these objects can cause some trouble in terms of our analyses. So if we look at the tax delinquency flag, so we'll go all the way over here. In this case, we have a lot of NANs, and there's going to be a 1, a 2. There will be a lot of different types of information in this tax delinquency flag. For the sake of this video, I will be intentionally dropping these. You can opt to use them if you can figure out how, but I don't expect that of anyone in this particular class. So let's go ahead and go down and start preparing our data. All right, so I'm going to pause here and walk through what we're doing to start with. First, we are taking the data frame that we loaded right here. So this is the data frame with 10,000 rows. And the first thing we're going to do is we're going to drop any cases that don't have a tax amount. This is ultimately what we're trying to predict. So if we don't have any information in this column, we do need to drop it. Then after we've done that, we're going to drop any columns that have any NA values. So we're going to drop rows that have NA values for the one thing we care the most about, tax amount, and then we're going to drop columns of information. So that is, for example, maybe latitude. If latitude had NA values, we would drop it in this particular case. So we're just removing NAs with this strategy. Again, you can test different strategies if it makes sense for you. This will give us a data frame that has that basically has no NAs in any of the rows or columns that we'll be using. The next thing that we need to do is we're actually going to define our X and Y just as we've done before. So let's go ahead and define our X. So in this case, we're dropping a number of different columns. So some of these columns, so tax delinquency flag, we're dropping this because it's an object and we don't want to be just coping with objects in this example. Some of these we're dropping because the data set that we'll be predicting to doesn't contain the information. So for example, in the test data set, we don't have information on tax amount, tax delinquency year, or tax dollar count. Those just don't exist in what we're predicting to. Some of these we are removing as well, like parcel ID, just because it's redundant information. We actually already have an ID field, so we don't need this. We also don't really have any reason to believe that parcel ID would be closely associated with our outcome. So this is our X variables. Another thing we're going to do is we're actually going to copy this, and we're going to print what columns are in our final data set. So we're just going to do the exact same thing, but here we're going to do dot columns. So when we execute this, first we'll create a new variable called X, which has everything in data no NA except for these variables. Then we're going to print what columns are contained in X, and we'll use this information later on. All right, two things I just added there. First was axis equals 1. This was a silly omission on my part. This tells pandas to look in the columns when it's looking for these. The second thing, errors equal ignore. So we do want to ignore errors here because when we do this drop NA, when we're dropping up here, these could drop one of, for example, we might drop the column, let's just look for one up here, fireplace flag. Fireplace flag is already dropped because it has NA values. But that might not always be true because we're taking a random subset of the data. And so we do want to ignore errors to account for that. So we're going to, when we run this, we then define X, and then we see these are the final set of columns in this particular case that we're including in X. So bathroom count, the FIPS code, latitude, longitude, property land use type ID, raw census tract blocks, region ID, room count, and then the normal ID. So this is what we would be using in our predictive model if we were to drop things according to this particular strategy. While this may not be the best strategy for dealing with NA values, I highly encourage you to explore other approaches. It will functionally work. So just consider that this is one area of the code that could be improved on. So here we're also going to define our Y variable. And this is just the tax amount. This is what we're trying to predict. So we can run this and that should work. And then we need to scale X. So we've talked a lot about data scaling. I'm not going to go into that here. We just need to define this. I'm going to copy this straight from a previous lab. And there we have it. So now we're going to have our standard scaler, our scaling model, and our X scale. Now we're going to, for the first time, do a little bit of ensemble modeling. So we're going to talk a lot about ensemble modeling in class. For now, what I'm going to do is I'm just going to copy a lot of code from a previous lab, which was the regression lab that we did. So in this case, it is a regression problem. We are trying to predict a numeric value, that is the amount that of tax. So I'm going to copy almost all of the regression models that we've done before. So this is all of these different regression models. Again, you can look at the exact detail of the code back kind of in our previous regression lab. One thing you'll see that's new here is the cross-val score. So this is just a cross-validation approach where we're going to cut our data into 5 different pieces and train with 4 pieces of the data and test on 1 piece of the data 5 different times. And the minimum here is just telling us to take the minimum of those scores. So what is the absolute best that any one of these estimators could do? This is just an idea. This will give us some estimate of how well we expect these different components of our ensemble model to do. We also have to do a little bit of importing to support all of these. So we're going to go and import all of these different regression models. And we're going to import this, the cross-validation score itself. Okay, so when we run this now, it will already work. This is simply the same format we've used before, and it will tell us for every individual model how strong those individual models are. Now, this is not ensemble at this point. This is simply saying individually, what is the mean absolute error that we are receiving? Now, one note here, this is the negative mean absolute error. There's a long story behind that. Ignore the negative. Essentially, this is what you are interested in. The mean absolute error you are receiving in these cases is, in this example, would be 2,711. 2,947. So random forest does outperform linear regression because it has a lower overall mean absolute error. So it will take a minute to run through all of these, depending on how you set your max iterations and other options. But then you should be able to see at the end, these are the individual results. So you can see a single classification or regression tree does very, very poorly. Overall, it looks like the regression forest is the best performing. Now we want to put all these together, and we're going to use an ensemble approach called voting regressors. So to do that, we're going to just simply take all of these different estimates for every single case and take the average. So we're going to, say across all of these, what is the average estimate for a given unit of observation? Again, I encourage you to explore other type of ensemble models. This is just a simple case for this video. So you can explore that if you go to ensemble. So if you go to the scikit-learn website, you'll see this is the voting classifier set. But if we then go to the user's guide, you can see there's going to be a large number of different strategies for kind of these regression cases. So you can look through the different, so here's a voting regressor, this is what we were just talking about. But you can look through the different types of strategies for ensemble modeling that you might apply. And if you just kind of explore these, you'll be able to choose the, explore if there are better cases than the voting. Okay, but back over here, let's go ahead and define our ensemble, and we're going to define it to include every single one of these models up here. So lasso, OMP, LR, RFR, so on and so forth. All right, and there we go. So this is our final ensemble model accuracy. As you can see, if you look at all of these individual models, all of them have a higher error than our ensemble model. So the ensemble model, in this case a voting regressor, was able to outperform all of these other cases. Now what we'll be doing is we're going to be taking this ensemble model and applying it to the test data set. So this is ultimately what we're going to be working with. because we don't know the answers for the test. So in this case, we are using the y variable that we defined up here. So that's the tax amount. For the test data set, we don't have that. So we need to use all of the x variables to predict. So let's go ahead and load in our test data frame. So now we can already see here, we have all of these different columns. We do not have tax amount. So if you look through here, you'll see there's no tax amount. We're missing a lot of information on the taxes. And so we have to work within those constraints. Now, the way we've defined our model up here, you'll recall, these are the x variables that we actually use to construct all of these different models, because these were the x variables that did not have NAs. So I'm going to go ahead and copy these. And what I'm going to do is I'm going to define our x test with those. So our x test is going to take from just the test CSV those columns of information. So if I run this, I will now have a new x test. This is an x test that is, I will have an x test for my test data frame. However, if I were to run this right now, it would not work. There are two problems. First, you'll recall that we scaled our data. So we have our scaling model up here. So we do have to scale this data. So let's go ahead and do that first. And you'll note, importantly, I'm not doing .fit transform, just .transform to do that transformation. And then we have to do one more thing. Not all of these columns have perfect information. So if we take a look at this, we'll just copy this test ETA. If we were to look through all of these columns of information, we would find NA values in some cases. We can't guarantee that our test database doesn't have NAs in a column. But we have to keep all of these columns. We don't have a choice because that's how we fit our model. So to fit that, we actually need to do a little bit of simple imputation. You'll recall much earlier in the class, we talked about imputation. So I'm going to use the sklearn impute model for this. And there we go. So we're all done. So what we've done here is we've gone through, we have the from sklearn impute simple imputer. All this is going to do is a column-wise mean. So if there is a missing value in a column, it's going to replace it with the mean of that column. And that's what we actually implement here. So x test scaled is actually going to contain both the scaled and imputed information for our model. Now what we want to do is actually create our predictions. So for every single row in test.csv, we want to predict what we think that the tax amount will be. So to do that is very simple. All we're going to do is we are going to first fit the ensemble model. So we're essentially doing the same thing here that we did up here, where we're just fitting all of the parameters for the different models. And then we just predict with it. So this gives us an array where for every single row, we have a tax amount that is predicted based on our ensemble model. Because we actually want to save this as a data frame, we're going to go ahead and this is for Kaggle, we are going to save our results as a CSV. We'll want to create a new data frame and then save it. So I'm going to go ahead and go down to a new snippet and create that. Okay, so you can go ahead and see here, we've now created a data frame where we have every ID and a column named predicted. Important that you keep this as predicted. And in that column predicted are all of the different predictions for those IDs. Now, we don't know what the truth is. The truth, we will only see when we upload to Kaggle how good this particular model is. So let's go ahead and save this as a CSV. And you'll see index equals false here. That's to prevent this. So this first column of data, this 0 through 99106, we don't need this, and it will mess up Kaggle when we upload. We only want ID and predicted. So we do index equals false. So go ahead and run this. There we go, that's completed. So if I go back to my ensembles, I now have my video estimates.csv. So I'm going to download this. And now I'm going to go back over to Kaggle. So on Kaggle, I'm going to click on Submit Predictions up here in the upper right. I've already submitted a baseline estimates.csv. I'm now going to submit a new one. So I'm going to upload here, and I'm going to choose video estimates.csv, what I just created. This will take just a moment. I'm going to briefly describe this as the estimates. And then I'll click Make Submission. So once I click this, it goes ahead and runs this, and you'll see that my current score is 2557. If I click this Jump to my position on the leaderboard, what we'll begin to see is over time, these leaderboards will expand to show these different scores. So the baseline estimate that I created, this is a very simplistic model that you will all see, is 2626. The video estimates that I was just able to create is 2557. When you create these, you'll begin to see how you stack up to the rest of the class. Now, importantly, you'll see the public leaderboard to start. What you will not see to start is the private leaderboard. The public leaderboard shows you based on 30% of our data. The final results are based on 100% of the data. And so you won't know what your final ranking is until everyone is done. Now, you're testing against 100,000 entries, so it won't change a lot. But if you're very, very close to the top, there may be minor perturbations. That's it. Once you're all done with that, you'll go to File, Download As, and you'll choose the .py. So you'll download this. You'll hop over into Blackboard and upload that particular .py file. Save and submit, and then once all submissions are done and we are past the end of the competition, I will be looking at the leaderboard, and your final grade for this lab will be calculated following this particular approach. So to describe that really quickly, overall, I'm going to calculate the median score that individuals are able to accomplish. Lower scores are better. Very important. If you score below the median, you will get a 100%. If you score above the median, then your score will be determined based on your the median divided by your score. So the closer you are to the median, the better a chance you will have of receiving a high grade. That's it. Good luck, everyone. I will see you in class.